Here are the solutions from 23 to 25 on the Kinematics review. 23, two of your friends are on a boat floating down a swiftly moving river. They have unfortunately run out of gas. You decide that you can drop a small container of gasoline into their boat from the bridge that is ahead. You are going to be dropping the container from a 75-meter high bridge, so we know how far the gas is going to fall. Notice I have a boat column and a gas column. You want to make sure whenever you're talking about two objects that you separate the kinematics variables for one and the other. Don't mix and match them. You get really weird answers. So you're going to drop it from the 75-meter high bridge and attempt to land it in the boat, which is moving toward the bridge at a constant speed, that means no acceleration, of 5 meters per second. What is the horizontal distance between the boat and the bridge at the moment you must release the container? So we're looking for how far away the boat is from where the bridge is, where you're going to be. Basically, how far is the boat going to move during the time the gas falls? So the only thing we know about the boat is a speed of 5 meters per second. What do we know about the gas? Well, we know that the gas is going to fall 75 meters. We know that we're dropping it, not throwing it, so the initial speed is 0 meters per second. And we know that once I let it go, the acceleration is negative 9.8 meters per second squared. If I just try and solve for the displacement of the boat, I don't have enough variables. I need time. And once you know it, the gas is going to fall while the boat's moving. These two times are the same. So I solve for the time for the gas, I'll have the time for the boat. So let's solve for the time for the gas. I'm going to pick the equation that does not have VF in it. That's D equals V naught T plus 1/2 AT squared. V naught is 0, so this term cancels out, leaving me with D equals 1/2 AT squared. I'm solving for time, so I'm going to multiply by 2 to get rid of the half and divide by A. That's why you have 2D divided by A. Take the square root to get rid of the squared, and I can plug in my numbers. Square root of 2 times negative 75 meters divided by negative 9.8 meters per second squared gives me a drop time of 3.9 seconds. I can now plug that in over here with my boat information and use our constant velocity equation of D equals V times T. So that's going to be 5 meters per second times 3.9 seconds for a displacement for the boat. The boat's going to be 19.6 meters away from the bridge when I drop the gas. Moving on to number 24. A cement block accidentally falls from rest from a ledge that's 53 meters high. You might notice that there's not 53 meters in the displacement here. Just wait and we'll talk you through it. When the block is 14 meters above the ground, a man 2 meters tall looks up and notices that the block is directly above him. How much time at most does the man have to get out of the way? Well, we don't have enough information in order to solve if we're taking a look at just when the guy notices. Now what I mean by that is if you just wrote down the kinematics variables, over here by the way, are the kinematics variables from the cement block once the guy sees it. It has 12 more meters to fall before it hits him in the head. Because it's 14 meters above the ground, but he's 2 meters tall. That's why it's a challenge problem. A couple little numbers thrown in to see if you're thinking. So it's going to fall 12 meters. We know the acceleration is negative 9.8 meters per second squared. But notice this 27.6 meters per second here, this negative velocity, that's nowhere in the problem because that's what we had to solve for. If you just try to solve it from the moment he sees it, you only have displacement, you only have acceleration. You don't have enough information to solve. So that's when we back the problem up. Starting from the beginning, it's dropped from rest. We know the initial speed of the thing when it falls because it was just knocked over. We know how far it falls because we can take that total displacement of 53, that's how high it was above the ground, and he sees it 14 meters above the ground. So that total distance that it falls is 39 meters, and it's negative, so we make that downward, and the acceleration is negative 9.8 meters per second squared. Well, the velocity it has when he first sees it is going to be the initial velocity at the point where he sees it, but it's going to come to the ground. So the velocity it has, 39 meters into its drop, is going to be the velocity it has 12 meters from the guy's head because it's the same spot. If you draw the picture, it's exactly the same. So we're going to be solving for VF. We don't have time, so we're going to be picking the equation that does not have time in it to solve for how fast this thing is going when the guy first notices it. We have VF squared equals V naught squared plus 2AD. Take the square root to get rid of the squared, and now we can plug in our numbers. VF equals the square root of 2 times negative 9.8 meters per second squared times negative 39 meters, giving us a final velocity of negative 27.6 meters per second. The negative is very, very important because you need an initial speed over here, negative. If you say it's positive, then you're saying when the guy notices it, it's moving away from him. It's flying up into the air, which is not what's happening. So now that we know how fast it's going when the guy sees it, we can break this problem into the second half, which is what's happening after the guy sees it. We know it's got 12 more meters till it hits him in the head. We know it's moving negative 27.6 meters per second, and we know the acceleration's negative 9.8 meters per second squared. From here we can solve for time. Pick the equation without VF in it. That's a quadratic of d equals v naught t plus 1 half at squared. We use our quadratic formula, which we talked about in previous problems, which t is negative v naught plus or minus square root of v naught squared plus 2ad all over a. And we plug in our numbers. Plug in our initial velocity, 27.6 here and here. We plug in our 2 times the acceleration. Got a little squished here, but you can still see it. 2 times negative 9.8 meters per second squared times negative 12 meters, all over negative 9.8 meters per second squared. And we get an answer of time of 0.41 seconds. That's how long the guy has to get out of the way before he gets cracked in the skull by a cement block. Number 25, a startled armadillo leaps upward. I don't know what scared him, but something did. And he rises 0.544 meters in his first 0.2 seconds of his jump. Now this is not a maximum height. Never said it was a maximum height, just said that's how far he goes in that amount of time. The question says A, what is the initial speed as the armadillo leaves the ground? B, what is the speed when he gets to 0.544 meters? And C, how much higher does he go? So here we go. First thing we'll solve for is his initial velocity. We know how high he goes, 0.544 meters. We know his acceleration, negative 9.8 meters per second squared, and we know his time, 0.2 seconds. All three of those numbers were given in the problem. I'm going to solve for initial velocity, so I'm picking the equation without VF in it. That's d equals v naught t plus 1 half at squared. I'm going to subtract this term, 1 half at squared, over to the left, and that's why I have d minus 1 half at squared. That leaves me with v naught t, but I'm going to divide the t out of here so I can get v naught by itself, which is why time is in the denominator. This time and this t squared do not cancel. Don't cancel those. Bad math. Don't do it. There's a minus sign here. There's two terms in the numerator. I can plug in my numbers, and I get 0.544 meters minus 1 half times negative 9.8 meters per second squared times 0.2 seconds squared all over 0.2 seconds. That's going to give me an initial velocity of 3.7 meters per second. So that's how fast the armadillo was moving when he first jumped. How fast is he moving when he gets to that point? Well, I'm going to pick an equation that does have v naught in it because they all do. I just chose the easiest one, the first one, which is vf equals v naught plus at. It's already set up for what I want. I just plug in my numbers. I get v naught is 3.7 meters per second plus negative 9.8 meters per second squared times 0.2 seconds. That gives me vf equals 1.74 meters per second. At that height, he's still moving upward. So how much higher does he go? Well, if I use the initial speed of 1.74 meters per second, which is how fast he was moving after he was 0.544 meters above the ground, his final velocity is 0, because that's how fast you're moving at the highest point of any jump, and acceleration negative 9.8 meters per second squared, and I'm solving for displacement. Picking the equation that does not have time, I get vf squared equals v naught squared plus 2ad. Solving for displacement, I subtract v naught squared over to the left, so that's vf squared minus v naught squared, divide the 2a, that's why they're in the denominator, and I plug in my numbers. 0 squared minus 1.74 meters per second squared divided by 2 times negative 9.8 meters per second squared gives me 0.154 meters. That's how much higher the armadillo goes.